Hey everyone, welcome to this video. So in this video, we're going to prove that E is an irrational number. I already made two shorts that go over this proof. You can find the links for these below, and if you really only have 1 minute, you should probably go there. Those videos do cover every detail, however, they go very fast. In fact, one of my friends pointed out to me that they're only a minute because I speeded them up so much, and that you can do anything in a minute if you do it fast enough, which is a fair point. So here I want to take a deeper dive to show that E is irrational. Take the number E, and we're going to expand it using the Taylor series. Remember the Taylor series for e to the x, we plug in x equals 1, and we get this sum of 1 over k factorial from k equals 0 to infinity, or if we write this out, 1 plus a half, plus a sixth, plus 1/24, and so forth. Okay? So now we're going to assume E is rational. And what that means is that E is equal to P over Q, where P and Q are integers, and Q is greater than or equal to 2, because E is not an integer itself. So now consider the number x equals q factorial times e minus sum k equals 0 to q 1 over k factorial. Okay? And it's really worth pointing out, notice that the number q makes 2 appearances in this definition. Okay? And of course that's the same q that appears there. All right. So remember, if E is rational and we can write E equals P over Q, then absolutely we can write down this formula for X. Okay. Another useful fact to point out is that because E has the infinite sum expansion, we can write this and notice I have two sums with the same summand but different limits. And so I could just write this as that. Again, I think it's worth pointing out, right, that if E is rational, and we can write E equals P over Q, then X can be defined in this way, and then so X exists. Now here's what we're going to show for the rest of this argument. We're going to show two facts. So the first fact we're going to show, we will show x is an integer. And the second fact we'll show is that x is between 0 and 1. Now, of course, no number can do both of those things, right? You can't have an integer strictly between 0 and 1. Therefore, we led to a contradiction. But what did we assume? We assumed that E was rational. So starting with E as a rational assumption and leading to a contradiction means that our assumption had to be wrong, and that E is in fact irrational. Now we want to show that X is an integer. Okay? Now to see this, let's first write X, just use the formula we have before. So this was just our definition of X. And now remember that we assumed that E was P over Q. And if we expand this out, we get this expression. Now, how do we see that this is an integer? First note that the first term is clearly an integer, just the way it's written. Secondly, recall that k is less than or equal to q in this sum, which means that q factorial divided by k factorial is also an integer. And since this term is a sum of integers, the whole thing's an integer, and there we go. So x is an integer. Now we want to show that x is positive. Recall the definition of x. We write it again like this. remember that E can be written as an infinite sum. And of course, we can subtract, since the sum ends are the same, we can write this as a single sum, just starting at q plus 1. And then finally distribute the q factorial across. And you see what we have here is we have a sum. Each term is positive, therefore the entire sum is positive. And we're done. Now we want to show that x is less than 1. So let's do a side calculation at first. So if k is bigger than q, then k factorial over q factorial is k times k minus 1 times k minus 2 dot 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 to q plus 1. So it's just a sum of a product of terms. And now let's ask how many such terms are there? Well, there's k minus q such terms. Notice that each term is larger than the smallest one, which is q plus 1. Therefore, k factorial over q factorial is greater than q plus 1 to the k minus q, right? Because if we just replace all of these terms by q plus 1, it gets smaller and strictly smaller, right? Conversely, just take the reciprocal of this expression to get a lower bound for this. Now what do we do with this? Again, recall our formula, slightly simplified. Okay. Now remember, if q factorial over k factorial is less than this is less than the sum k equals q plus 1 to infinity, 1 over q plus 1 to the k minus q. Okay. Now, let's do a change of index. If we write L equals k minus q, well then notice when k equals q plus 1, L is 1. Of course, when k is infinity, L is still infinity. So this just is rewritten as L equals 1 to infinity, 1 over q plus 1 to the L. And now we just use the formula for a geometric series. And when we sum a geometric series starting at 1, we get this expression here with a little bit of algebra. Notice if I multiply everything through by q plus 1 all over the place, I get 1 over k plus 1 minus 1, which is 1 over q, which is less than 1. And we're done.